Students, it's good to see you again. I hope that your week has been productive. Today we are going to be talking about teaching and learning number, because mathematics use symbols, and the symbols they use are numbers. And so therefore we have to learn efficient strategies to improve or to help to improve the skills of our students. When students begin secondary school, they have had many years of schooling and they have experience with number. It cannot be escaped. Most students associate mathematics with numbers and they readily appreciate the application of numbers. For instance, we have students who appreciate area, the whole concept of area or perimeter, or volume with numbers. It's a number that tells us what we want to know about the volume or the area of a entity. Secondary schools, as in primary years, number concepts are still needed for other mathematical domains. For instance, the telephone and the computer that we appreciate so much in our lives come to us through this binary system where we have 1 and 0. It's like a light switch. If it's on, probably we say that is 1, and when we flip the switch, it becomes up O or 0, where there is no in between. There are no fractions. It's either 1 or 0, 0 or 1. By the end of primary schooling, children have learned the underpinnings of the concept of whole numbers. And unless we do a very good job with fractions, they might come to the place where they have to learn fractions with a concept of whole numbers still in their heads, and they do not make the switch. That is our job. We're supposed to allow them to make the switch. Just to give you an example, and we'll come back to more examples when we talk about fractions. But say we're looking at the fraction 1/2 and 1/8. Because students come to us with the understanding, and rightly so, that 8 is more than 2, 1/2, they will say, is less than 1/8. I will only say that for now, because we'll be coming to deal with fractions as a topic. The instruction that they receive in primary school is supposed to be a base on which we can build secondary school mathematics. But often we find that students come to us not as prepared as we would like them to be. And so it is our job, we have a big job, it's our job to do a diagnostic test. And many schools in Jamaica give a diagnostic test to the incoming 7th graders in order to determine their level of proficiency with many skill areas. Hence, they give what is called a diagnostic test. This is not a test that will be recorded for any report card. It's just something to indicate to the teacher the level of students that we get, because you know as well as I do that even at the 7th grade level, straight 7th grade level, we find that there is a variety of skill levels within the 7th grade branch, within the 7th grade level of the school. And so they're coming in, they were judged appropriate to come to your school. Even in a 7th grade class, there are many different levels of proficiency. But we are supposed to be building on their store of knowledge. So the diagnostic test serves the purpose that as we give those tests and we determine where the weaknesses are, we need to stop everything we're doing and strengthen those areas, because the job will be easier to pile on something on a sound foundation. So we have to develop efficient strategies, as I said before, to improve the skills, because they will have a full range of numbers to deal with in different contexts at the secondary school level. In this chapter, we will focus on the curriculum as it comes to us, but we know that we must have a foundation, and so therefore we have to spend some time to do this. We will focus on concepts and skills that are important for mathematical literacy and success in senior secondary mathematics. We will not go into the mathematics that deal with complex numbers or matrices. What we will do include place value, fractions, mental computation, multiplicative thinking. For instance, by multiplicative thinking, I mean that if we have a whole number multiplying by a fraction, many students do not understand why it is that you're multiplying and getting a smaller number. For instance, if I multiply 5,000 by 1/2, we are going to get something smaller than 5,000. But kids sometimes get the concept that is cemented in their heads that if you multiply, you must get a larger number. We will be thinking of proportional thinking also, and that has to do with percentages. You want to check? We'll be looking at exponential thinking. We'll be looking at some irrational numbers, and of course, integers. Our students coming from the primary school level will be steeped in knowledge about whole numbers. Sometimes they find the concept dealing with integers to be somewhat difficult. So we will be looking at ways to facilitate their learning in this area on this topic. We know that as secondary students, they will have to understand and develop mathematical thinking. Mathematical thinking is a concept that applies across the mathematics board. For instance, number sense. Number sense can be applied in any area. Number sense is the state of mind that we cultivate in our students, that they have a sense of what is happening if we multiply. Why it is that we get a smaller number when we are multiplying. They need to know that kind of thing. So here we are going to be looking at numbers in the primary years. Primary teachers use a range of materials and learning aids to assist student learning of number. These concrete materials help students to understand and visualize the concept in multiple ways. So if we're presenting some information and we sing it, we illustrate it, we fold it, we rotate it, we do everything that we can do, both mentally as we form the mental structures and both physically as we actually handle some manipulative to explain the concept. We know that there is a greater chance of it being understood conceptually. Why materials are important? They connect mathematical symbols and language with the concept. Younger children learn by rote, then afterwards they count by ones, and afterward they associate one to one. In the early years, primary teachers then build more efficient strategies for adding, using the part-to-whole concept of number, counting from a larger number, doubling number, building tens to establish addition and subtraction facts. You may observe that some secondary students are not proficient still use counting by ones, like they will use their fingers, they will you could see them doing this when they are working with numbers. Children begin to understand fractions and decimal in context and model them using materials in primary school. They continue to use the concrete materials in early secondary school to assist them in understanding equivalence of fractions and decimals. To compare and order fractions and decimals, to understand operations with fractions and decimals. So they learn what they are, they learn how to order them, they learn how to do operations, add, subtract, multiply, and divide. Sometimes teachers use fraction strips because it's easily made. Students can go through the experience of making their own in order that they will understand that if I have a bar that represents a whole fraction, if I place that same bar or that same strip folded in 4, we see that 4 1/4 make 1 whole. In the upper primary school, children extend their knowledge to base 10. They understand that we have 9 digits to make our 10 digits to make our number system 0 through 9. Through a range of application tasks, they develop a sense of very large and very small, and they learn to compare them. Now, comparisons made by students have they have very good understanding at the primary stage about that, especially if the numbers are far apart. Suppose I say 10 and suppose I say 100. Most primary schools students will make the connection that 10 is smaller than 100, or going the other way, 100 is larger than 10. Now, we also need to develop number sense. And I'll be saying this over and over and over again. We must have some mental math in our heads that when we see a situation, as we begin to estimate, to do some of the operations, to just establish the ballpark, then we will develop our number sense. Number in the secondary years. In the secondary years, students consolidate and extend their number sense for solving problems and making judgments. That's the word, making judgments. If I do this times this, that number could not be this large. Or we do not know exactly what the number is, but the number we have on paper causes a light bulb to come on to say, this does not look like a reasonable answer. So when we have number sense, we are able to make judgments. So in order to get this number sense, students should be able to calculate mentally. They should be able to calculate mentally. Use approximations, as I said, to estimate. Understand the connection and relationship between numbers and use them when calculating. Now, they also should have a sense of the size of a number in relationship to other numbers. They should be able to say to themselves, if I multiply 1,000 by 10, I should get a reasonably larger number than a smaller number. They should understand the concept of multiplying by 1. They should understand the concept of multiplying by 0. And sometimes students, even in the secondary schools, are not on their feet when it comes to multiplying by 0. They should be able to switch between equivalent representation of a number. For example, 1/2 is not equal to, but equivalent to 2/4. Students in secondary schools also learn about other types. They have sets of numbers. For instance, They might or might not have had any introduction to integers in the primary grades, but surely they are introduced to the integers in the secondary schools, and they have to work a great deal with them. Rational numbers. In primary school, the students call them fractions. Here we call them primary, we say unit fractions when we're dealing with some, but in general, we put them in a group, call them rational numbers. We also have irrational numbers, real numbers. And for some students, they go on to complex numbers. A study of students in the middle years found that many students had difficulty with explaining and justifying mathematical thinking. A lot of times, a student will come to me with a problem, and I will say, how did you get this? Can you explain the process? No, miss. No, miss. I just know to do it. I can't explain it. I can't explain it, miss. So sometimes I say, why can't you explain it? I just did it like the teacher did it on the board, miss. And that is not good enough for us as teachers, because we're striving to something beyond the correct answer. They have difficulty with reading, manipulating, using common fractions, decimal, ratio, proportion, and using formulas. Many of my teachers and many of my students as well do not write a formula as an equation. For instance, we are having dialogue with our students in class about area. Area of the rectangle is, they write on the board, L times W. L times W is only half of the equation. We need to write area is equal to, in words spelled out, area is equal to length times width. Furthermore, there are considerable range of achievement levels, as I mentioned before, among students in the same grade level in the same class. So they have this range of achievement at that level classified as the 7th grade. Some Seaman person who did some research recommended that teachers in the middle years focus on speaking and listening among students and teachers in the mathematics classroom, and on building meaning and making connection between ideas. There is something called cognitive overload. Cognitive overload has to do with bearing the burden of learning everything as an isolated entity. But it's like having fruits in a basket. You can pick them out one by one. But there are so many structures to understand and learn about in mathematics that it would be better if we could establish some linkages between them. If we could see some equivalence, if we could see some application that could be applied to this and the same one applied to that, then we could put these ideas on an umbrella and we classify them so that instead of putting one thing in isolation all the time, but in the same brain, we would have an entity that is a composite, that is linked by a common fact or a common attribute or a common number or a common idea. And then we would not go into cognitive overload. I told you that we are going to be talking about whole numbers and how it intersects with some other things a little bit later. Because there was no intersection in our minds, or we did not lead our children to think that, they get into serious trouble. One thing we have to think about is place value. Place value. Understanding the value of digits in their place in a number is the basis for counting and comparing numbers. As I said before, if the numbers are far apart like 10 and 100, we do not have any problems. But we have a lot of problems with fractions. We're comparing. Children in the primary years learn that values are based on multiples of 10. The 0 is the placeholder, and that the decimal point is the marker that separates whole numbers from fractional parts. In our culture, now we have learned that if we have 100,000, we do not write 1, 0, 0, comma, 0, 0, 0. What we learn is to leave a space. That is something new. Some people use commas, and so I know that sometimes in the Spanish-speaking countries, they use commas. With the aid of place value chart, saying aloud the place value when reading decimal numbers will help students to have who have difficulty with comparing decimals. For example, 31.265 should be read as 31 wholes, WHOLES, and 2 tenths, 600s, and 5 thousandths. Because with this kind of practice, they will be saying the place value. They will be saying the place value. Because what we read most often is 31.265. They have no mention of place value. So we say 31 wholes, 2 tenths, 600s, and 5 thousandths. They are saying it. They are repeating it. They're speaking to their brain to retain it. And so they have anchored themselves by using that kind of language. The approach will also help students to interpret large numbers that are common in the media. A lot of times in the media, because they're who they are and they get information from companies that operate with large numbers, they will say 1.2 million. They will say 3.6 million. We are aware after a certain point that we can express these numbers in scientific notation, or we can use for smaller numbers, we can use the expanded notation. So if we have 316, we could write 6 times 10 to the 0 plus 1 times 10 to the 1 power, first power, plus 3 times 10 to the second power. And in that case, we are looking at place value, and it's being cemented. When we close our eyes, we can see them. Now, I want you to listen carefully. I'm going to speak slowly so that you can understand this. A child, a student, was given 3 pairs of numbers that included decimals. One pair, first pair, write this down, 1.053. Its partner is 1.06. I hope you have gotten that. The next pair is 4.08 and 4.7. The third pair, 3.72. The To complete the pair, we have 3.073. Now think about this. I want you to circle exactly what the student circled. From my chart, the student circled for the first pair. What they have to do is to circle the number that is larger. Let us get the instructions straight. Circle the one that is larger. So I have a left column and I have a right column. The student circled 1.053. Next pair, the student circled 4.08. And the next pair, the student circled 3.073. Here, there is a great misconception because the lack of appreciation of place value. Misconception arises from a number of reasons. Our children are coming to us steeped in whole numbers. And we know that a 4-digit number must be greater than a 1-digit number. That is what we understand. And so therefore, it is a carryover. And one of the carryover, longer must be larger. Longer must be larger. And so they circle the longer number. Students who think longer is larger is using the whole number thinking. And it's generally a source of misconception for fractions, as I mentioned earlier, and will embellish later. The shorter is larger fallacy has occurred after students have been introduced to negative numbers. And these students have difficulty placing decimals smaller than 1 on the line labeled integers. These students seem to think that decimal numbers are below 0 or negative. Linear attribute blocks that show students the value of digits in decimal numbers, together with open-ended investigations, games, and application problems related to familiar context for students, improve student knowledge of decimals. So we see that we have a job to do. We need to know that our student can discriminate between two numbers based on place value. Longer is larger only happens probably and sometimes not in whole numbers, because 5,000 and 1,000 have the same number of digits. But they should appreciate that 5 is larger than 1 and choose 5,000 as a larger number if they were given that task. What you should review and reflect on is that you're to develop a set of materials and tasks that will be suitable to use with students whose responses are like the ones that are recorded, and we just worked with that. Now we move on to fractions. While students have been learning about fractions since the early years of schooling, conceptual understandings and operation with fractions are difficult for many students at the secondary level. And just a secret between you and me, some teachers have problems with fractions, even though they have been in the classroom for some time. most students. What is a fraction, students? Part of a whole, a part of a whole, a part of a whole. They will say that, rather than seeing that a fraction could be a part of a collection of things. It can be groups of. How many groups of blank can I get from blank? They want to deal with fraction with one unit, separate the unit into equal parts. That's the end of the fraction story for some students. But if we have 35 things to share among 7 people, that concept becomes foggy with the students. We have a situation with students who are at risk in the secondary schools. They do not accurately illustrate equal parts when drawing models of fractions. So for instance, a circle presents illustrates a familiar misconception. We have a circle to be divided into 4 equal, 4 equal, 4 equal. They divide the circle into 4 parts in any which way. Sometimes it's straight down, and given that it won't be to scale and everything, but it's clear that they do not understand the concept, because if you make strips on a circle from one point on the circumference to the other and make 4, you will not get 4 equal parts. And so they have many, many problems with that, especially if they get into separating other figures than maybe squares or rectangles. They have problems modeling improper fractions. Here again, they have problems modeling improper fractions. Say 4.5 or 4 1/3 or whatever. But when they would be able to get to 4 or 5, depending on what the whole number part is. But when they are now to make the thirds or the fourths or the halves, therein lies the problem. And so they do not know how to express 4 1/2 graphically on the number line. The thing is that they are shaped differently, and we have to undo that shaping with the kids who come into, or the students. I say kids all the time, I'm sorry, but with students who attend our classes. Making sense of fractions also means that students are able to compare fractions and find equivalent representation of fractions. Comparing larger, smaller, larger, smaller. If they, as I mentioned very early in this lecture, if they see 1/2 and 1/8, by George, 1/8 should be larger because 8 is larger than 2. So they would put the inequality sign in the wrong direction because they're steeped in whole number orientation. Fractions modeled using paper folding to create models such as fraction strips and rectangles and fraction walls made up of multiple fraction strips can be used for open-ended investigation. Find 10 fractions that are equivalent. So if we have a rectangle and we draw equal parallel lines, equidistant parallel lines all the way down, we can have the top one as a unit, the second one divided into half, third one divided into thirds, and so on. If we are in the early years of the secondary school and we find out that our children who are coming from the primary are not well versed in this, it would pay off dividends in a large degree if we spend some time correcting any misconceptions that they might have about fractions. Now, when it comes to multiplying fractions, we can formalize these investigations through discussion and create facts for our students to enable them to appreciate that equivalent fractions are formed when multiplying or dividing by 1. Now, that is a keeper. We have 5, 6 to be expressed equivalently. If some of my children see 3 over 3, it has to be explained to them that this is a 1, because any number divided by itself gives 1. And so we can create equivalent fractions by multiplying by any number in the numerator and the same number in the denominator to get an equivalent fraction. And what we can do to concretize that for them is to have the fraction bars. So when they lay the 15, 18, probably not high up like that, you would want to have like 2 quarters, which is a half, laid on the half. So you will have that and show them that you can get an equivalent fraction. That 1/2 equal to 2/4. Start there. Do not start where I was about to say something about 15 16ths and that kind of a thing. Just start at the beginning where they're able to manipulate and they're able to work with the concept using some manipulatives. Again, students hang on to whole numbers when they are dealing with fractions. And take, for instance, write this down, 2/3 and 7/10. Some of them have argued that 2/3 is larger than 7/10 because the numerator in 2/3 is 2, only 1 away from the denominator, which is 3. And 7 is all of 3 numbers different from its denominator. We should be having dialogue with our students to determine that these misconceptions are cleared up. So that's why I want you to write this down in order that you might bring that up as one of the ideas to debunk if you find that your students are associating that kind of thinking when comparing fractions. Just like they develop their whole number sense, they should be developing their fraction sense. Students need to be able to visualize fractions that are nearer to 0 than it is to 1. Sort of get them to think, is it below the middle? Is it above the middle? Similar to what we do when we're doing with rounding. If I had this unit strip and I shared it in 2 equal parts, each representing a half, and I have a decimal number, because a half is really 1/5, 0.5, sorry, 0.5. A half is really 0.5. Let me say that clearly. A half is equal to 0.5. If we have a fraction that is somewhere beyond 0.5, it should be in the upper half of the unit. And so we have to assist our students to get that understanding. Now, encourage students to use visual images and estimation. I say that again. Encourage students to use visual images and estimation. Picture these two sets of fractions. Write them down. 4/10, 4/47, 4/8. 99, this is one group. 99/100, 6/7, and 15/60. They are looking at estimation and they have to order the fractions. Order the fraction. This is the instruction. Order the fractions in each set from smallest to largest. Explain the visual images, where we have them written down so they can see them. Explain the visual images and use to order these fractions. When you see these fractions, what is the discussion that comes up? That would be a good thing for you to try if you are working with fractions related to any topic at this time. Now, another thing here to do. Use 4 of these digits. 1, 3, 4, 5, 6, and 7. Again, 1, 3, 4, 5, 6, only once to create the sum of two fractions that is less than but close to 1 whole. What did I say? Use 1, 3, 4, 5, 6 to create the sum of two fractions that is less than but as close to 1 as possible. So that's what you're supposed to do with your kids. And get into a discussion. That would be the trigger point for get into a discussion about the fractions that are close to 1 or furthest away from 1, and you will get a sense of where your students are with this kind of process. Maybe afterwards, after discussion is over, you could ask your student to evaluate, to say what they have learned, if anything, to say what they have remembered, if anything, because these are so important. You have to use these trigger points, these launch pads, like this one I just gave you, to generate a discussion, and you will be surprised at what you will find out as the students participate. The other topic we are moving on to, which is not specific, but is generally applicable to all areas of mathematics, is mental computation. Mental computation. It cannot be exaggerated how important this mental computation is for us as teachers and students. Remember, today's topic is teaching and learning number. Teacher and student discussing, discovering, changing our minds about things, enhancing our skills as we talk about mental computation. Mental computation is the ability to use number facts and number sense to solve operations without the aid of a computational tool like a calculator or pen and pencil. Pen and pencil are our friends. We use them, we finish them, we start another one, because we are so addicted to the pencil and paper. The ability to compute mentally is more than automatic recall. When we have the situation of computing numbers like adding, subtracting, multiplying, and dividing, we need the ability to compute mentally in order to be efficient thinkers. It has received a lot of attention in some quarters, but not all of them. The emphasis resulted from research show that adults use mental images and computational tools such as calculators more often than pen and paper algorithms to explain and calculate with accuracy. Teaching materials have been developed for the primary and middle years, but secondary textbook writers have paid scant attention to continuing development of effective and efficient mental computation strategies with whole numbers, fractions, decimals, and percentages. Students who use mental strategies demonstrate understanding of field laws. Field laws, what we call them? Field laws are what we talk about when we look at some of the postulates, where we know that if we have mental computation, we have 5 times 7 is 35. Switch it around, we have 7 times 5 is 35. If we learn our multiplication table and we have 36 individual cells that are filled, 36 individual cells that are filled. If we find a way to make it 4 rows of cells, we have cut down on, instead of having 12 rows, we now have 4. I think that is a very good discovery. Just to give you one of them. If we know our 2 times table, we acquire 4 times table for free. Because all we have to do is if you want to know what is your 4 times table, practice your 2 times table and double it, you're at your 4 times table. So we have done that, right? Now, if we were able to see the links, or we were able to show our students the links in that regard, they would not have such a difficult time learning their times table. We have 3 times table, and those are pretty easy. Most people know that. If we doubled our 3 times table, we would know our 6 times table, and voila, we would know our 12 times table. So what we need to do is to make those links so that the student does not have to carry around 36 pieces of information isolated in our head just for the times table. No wonder they find it difficult, because we present it in that manner. The secret of field laws, again, are kept away from students, like the commutative property. 3 times 5 is the same as 5 times 3. So if we know one, we get the other one free of cost. Free of cost. And that will help us with the mental computation. So to be profitable for you to talk to your students about their mental strategies and help them to see that they can use that to cut down on cognitive overload. Let us look at now multiplicative thinking. Multiplicative thinking associated with our multiplication table. But where we get into a situation where we have the whole concept being discussed in isolation to hands-on. We could use some strips, we could use tiles, we could use blocks, we could use all those things to show our students that we can illustrate the properties, the field laws we call them, the field laws to make their burden lighter. Multiplication of fractions and decimal, we have a great deal of trouble. We have a great deal of trouble because, as I mentioned earlier, a lot of our kids, if you give them two numbers to multiply, start with pencil and paper, labor intensive, they work it out. But when you get to decimals, they do not know what to do. But take, for instance, if we had developed some mental capacity around this multiplication, we could say, to dealing with whole numbers, we could say you do not have to get a problem incorrect. Because if you started by estimating or just try out the two numbers that are in the highest place value, we would establish a ceiling on what we have to do. And if we go beyond that in error, that would provide a check and balance for us. Let us take, for instance, 3 point whatever you want it to be times 5 point whatever you want it to be. Try an experiment. Make it 3.2 something. And make it 5 point smaller number than 5. What we have to do then is to encourage our kids to say, if you're multiplying, you have 3 times 5. Those are the largest numbers according to place value that you have to deal with. So if you test out 5 times 3, you're going to get 15. That is sort of establishing a ceiling on what we can get for this problem, especially since the decimal part is now smaller than a half in both instances. Hope you understand that. Now let us go a bit further. Suppose I have 3.7 something something. 5.5 something something. I would still use my 3 times 5 to give me a feeling of where I'm going. But since I know that the decimal part is greater than a half, I know that my ceiling could not be 15 because I must manufacture some whole number by using those fractional parts that are greater than a half. So here I am, but I'm still in the ballpark. So I expect 16 point something something max, maybe 17 point a little bit. But the thing is that with the number sense and the ability to compute mentally, I will know that my number cannot be 25. I am trapped somewhere in the 15, 16 range. So if I make an error with my multiplication, I can catch myself. And I do not have to send a problem with an incorrect answer to my teacher. Teachers, it is incumbent upon us to help our students to be effective. Now, let me say another thing. Generally, when we introduce multiplication of decimals, we have to tell them what direction to come from to establish the number of decimal points. Sometimes they get it mixed up. Or we say if the first number has two decimal places, and the second one has one, then we must have three decimal places. But if we are looking for a 15 or a 16, we do not have to tell them anything about how to find it, because they know the decimal point must be counting from left to right, the same direction in which we read, must be behind, two digits must be behind the decimal. After the decimal, whatever is there, that's what it should be. We do not have to confuse them, because some students do not know when we multiply the number without a decimal point, if we have to count from the left or we have to count from the right. So here we are. We need to help our students to appreciate these measures. Where we stop this evening is to talk about dividing by fractions and dividing by decimals. I mentioned it earlier. We need to put the division by fractions and multiplication by fractions in context for our students. They do something mechanically. They do not understand what happened while we have to flip when we are dividing by a fraction. They do not understand when we are multiplying by a fraction. While we are multiplying, but we're getting a smaller number. We need to put that in context for them. As again, when we divide by fractions, we need to talk about how many groups of. That's in quotes. How many groups of. We need to talk about that. The measurement of meaning, the measurement meaning of division. The measurement meaning of division. Or else, otherwise, students have difficulty thinking about dividing by fractions. For example, what's the understanding between 9 divided by 1/4? Fraction strips could help. If we embrace them on a grid paper. For your class, you should really have like 10 by 10 grid, 100 square grid of a reasonable size that all of your students can benefit from it once it's placed on the board. Okay? So what we have is a class representation, and they individually should be holding a smaller 100 grid in their hands, because now they're going to have hands-on, and hands-on means brains-on. Okay? So here, if we look at it, we will see what 9 divided by 1/4 means. Okay? When students solve fraction division problems that are placed in context, they will have a good understanding of why this thing that is 9 divided by 1/4 turns what? It's going to be, you give the answer. Okay? Now, context is very, very important. And we want our students to appreciate that. Okay? Now, proportional thinking, and then we'll stop. I said we were going to stop at division of fractions and decimals. So here we need to engage them with multiplicative thinking, and then we need to engage them with dividing by fractions using a manipulative. Okay? Proportional thinking is the next thing and the last thing. Proportional thinking involves making sense of quantitative relationships and comparing quantities that have a multiplicative relationship. Ratio and proportions are used in real situations. We need to have substantial dialogue about how it is used and the benefit we reap from this. They underpin and connect mathematical ideas in secondary school mathematics. Learning about ratio, proportion, and percentages provides lots of opportunity for engaging students in authentic tasks and in problem solving. We could bring up the whole fact of census taking. What percentage of our population, based on the reports, is a group of people who are between 17 and 25? What do we do with that information? Why does the government take census in the first place? Suppose we find that 40% of our population is a group that consists of senior citizens. Does that have any implication for policy planning? We don't have to call it policy planning in the lower grades if they do not understand. But ask, what would the government do with that? And let them brainstorm, because we have proportional thinking. If we find out that a large chunk of our population are senior citizens, then the money that we reap from taxes need to be spent in a different way than if we find the same 45% are people between the ages of 17 and 25. For the older people, we have to look at health services, for instance. We need to look at availability and accessibility of nearby clinics, because we do not want somebody in a wheelchair to be going forever somewhere, especially if they do not have a car. Our buses need to be wheelchair accessible. All those kinds of things would come in, versus if we have a population of 40% where the students are, the people are students, because between 17 and 25, we have late high school students and we have early adults in the workplace. So we're going to need universities, we're going to need more high schools, we're going to need opportunities for the labor market. We need so many things, and so therefore we need to have the professional thinking. Measurement in geometry in the classroom is associated with the idea of proportional thinking. We know about the fact that any two sides of a triangle, the sum of them must be greater than the third side. And of course, we know that a triangle has 3 sides. But the thing is, though, we cannot have anything that is so important to be hidden from our students, not connected to any reality, and stored in little compartments like eggs in a carton. We need to have an omelette. So here we have a situation now with ratios. Ratios are everywhere around us. If we are in a room and all the seats are taken, and the ratio of seats to people is 1 to 1. We want the situation to be placed in a context where our students will understand. And so ratio now connects to proportion, because the equality of two ratios gives us a proportion. We must make these connections with our students. We need to know that they want to make sense of it, and we should help them. Percent is a particular type of ratio. 50 out of 100. 35 out of 100. We must help our students to understand that 100% can be represented by any number. We can put it in context for them. We say our school here, our 100% attendance in school must consist of 1,200 students. But the primary school next door, they have 100% attendance if their student population is 850. So here we are. Percent, 100% can be represented by any number. And that it is a great equalizer, because in one country we have 350 million people. In Jamaica we have 2 million people. That's our 100%. But if we speak about percentage of people who use Colgate toothpaste, we can find a comparison between the usage of the people in both countries that are readily available to us through percentage. So these things, our students might not see them, but we have to make some link that they can understand. If I say 50% of the students in Jamaica use Colgate toothpaste, that would be equal to a different number than the country that has 20 million people. But proportionally, it would be the same. That link is there, it's glaring, it's something that we must do for our students, because we want to have the children learning math in a meaningful way. And that's where we're going to stop today. Thank you so much, and have a good day. Bye-bye.